What I'm going to talk to you about here in this video is working with 3x3 systems and matrices using a technique called back substitution. Now this is a technique that allows us to read off an answer and a set of solutions to a set of equations and a system of equations if that system obviously has a set solution. Now we know about getting into upper triangular form. So we know about getting a matrix into upper triangular form where we've got set values here for the letters A to F, but the bottom left triangle, corner if you like, is just zeros. What back substitution allows us to do is take this matrix here and transform it such that we're left with essentially the 3x3 identity matrix on the left hand side as part of our equation, with solutions A, B and C here, all determined using elementary row operations. Now the good thing about it here is that if I were to have it in that form, I could instantly read off the solution for X, Y and Z that satisfies my system of equations. So this back substitution technique allows us a quicker, more efficient way of reading off a solution. But we need to know how to do it and the way we work it through. So I'm going to show you an example here. Now let's imagine I've taken a matrix, this one here, I've done a bit of jiggery pokery to it, and what I now have is I have the matrix here in this format. Now this is upper triangular form. I could read the solutions off and work it through if I wanted to. However, what I'm going to do is take this and I'm going to use back substitution and row operations so that I can modify this diagonal here to be 1, 1, 1. The rest of the entries to be 0 in this side. I'll have some solution over here, and then it's a case of I can read it off. So if I start by taking this and I make row 3, whatever row 3 is now, divided by negative a third, and I do row 2 being replaced by negative a half row 2, what that's going to then mean is I've got 1, 1, 1 in my top row with a 2. I've then got 0, 1, 0 here, and I've got 0, 0, 1 down the bottom, and this is going to be 1, and this is going to be 2 here. What I can now do is use back substitution in order to be able to get rid of these values here. And what that means is I now do row 1, take away set values from each row. So if I was to do row 1, take away row 3, what would happen is this and this would take away, and I'd be left with a 0 here. Now normally, when we're doing that, there'd also be some modifications to X and Y. But the good thing is, because I'm taking away row 3 from row 1, I have 0 in these two elements already. So nothing is going to change with these. The other entries, so this one here and this here, may change depending upon the row operation, but these entries themselves won't. So if I were to do that and do row 1 take away row 3, what I'd end up with is 1, 1, 0. I then have 2 take away 2, which is 0. I then have 0, 1, 0, 1 for my middle row, and my bottom row, row 3, again would remain exactly the same. And what I can then do is do the same thing going back the way by doing an operation onto row 1 and saying if I do row 1 take away row 2 and put that into row 1, that is going to eliminate this middle one here, and by the same logic as I talked about here, nothing will happen to either of these two values, so my top row will be left with 1, 0, 0. So what that then means is I'll get 1, 0, 0, and I'll then have 1 take away that, so I'll have negative 1. I'll have 0, 1, 0 and 1, and I'll have 0, 0, 1 and 2. So now that I've got that there, I can actually just quickly, simply and efficiently read off the set of solutions. So what I can tell you now is, remember, we have to make sure we know what the columns in here represent. So I know the first column represents X's, second represents Y, third represents Z. So from that I can say to you, fine, so X is negative 1, Y is 1, and Z is 2. Job done, I've got my solutions. So it's a technique that allows us to do that. Now, it may not be necessary to do it in every single example and every single bit of working. However, it may ask us to transform it into the identity matrix such that we can just read it off. Or it may be a requirement that we have to use back substitution in order to solve it. So it's a technique we need to be aware of. Exactly the same as elementary row operations, except we're working back up the matrix in order to eliminate the elements in row 1 and row 2 if needed, such that we can then get it. For example, if I had an element here, let's say I ended up doing my calculation and this element here was 1, what I would then do is row 2, take away row 3 to eliminate this element here. So when we're doing back substitution, it's both rows that could be taken into account. So we'd use the third row to get rid of elements in this, we'd then use the second row to get rid of the second element in the first row. Fairly straightforward. As long as we follow the general idea in the steps, you'll be fine.